Hello, in this video I will be reviewing a past exam for MATA37 from April 21, 2017. So we have some true-false questions, and justification is not rewarded. So suppose the sequence AN, which is contained in R, suppose the AN is contained in R, is a sequence that's contained in R. If it's bounded for all of its terms, and its limit approaches 0, then the sequence converges. AN is bounded, and the limit, if the limit is 0, then it's definitely bounded. That feels kind of like redundant information, right? It's just a bunch of real numbers that's going to 0, so it doesn't make sense that it would be unbounded, but whatever. But just because the general term approaches 0, it does not necessarily imply that the series converges. It might, because it satisfies the vanishing condition, but that's not enough to guarantee convergence. Like, for example, in this case, the general term is obviously bounded, because if the limit is 0, it will definitely be bounded, but it diverges. It's the harmonic series, or P series, with power equal to 1, which is less than or equal to 1. Okay, absolute convergence implies conditional convergence. This is false. Absolute convergence implies convergence, but conditional convergence generally is the opposite of absolute convergence, so absolute convergence implies not conditional convergence. Because absolute convergence means that this one converges, right? Conditional convergence means that this one diverges, but this one converges, right? So this one will definitely converge, but that's not what conditional convergence means. Okay. The curve y equals that is decreasing everywhere. So we have to check this by doing the derivative and seeing if the derivative is negative everywhere. So we're gonna have to use fundamental theorem of calculus 2 to find the derivative of y. So we see here that this is just f of t right here. So we're also going to have to use chain rule. It's important that our function is continuous from 0 to minus 2x. However, we know that t squared over t squared plus 2 is continuous over r, because the denominator is always going to be a positive real number, because t squared is 0 or more, and t squared on top is also a real number. So we're fine. So therefore we can use chain rule and fundamental theorem of calculus 2. So basically we can plug in the minus 2x into the function. Can do minus 2x squared over minus 2x squared plus 2, and then chain rule we have to multiply by minus 2. Basically, the way you can think about this is that the theorem states that if it's from 0 to x, then you can just plug x into the function to get the derivative of the integral of the accumulation function. But in this case we have minus 2x, so when we take the derivative we have to first take the derivative of the outer function, which is the accumulation function, then take the derivative of the inner function. Okay. So now we see that for any x, if x equals 0, then y prime is 0. But decreasing means that y prime is less than or equal to 0. If it were strictly decreasing, it would be false, because at the point x equals 0, this curve is just it has like an inflection point, right? But because they don't say strictly decreasing, just decreasing, then that we don't care about inflection points. We just care that the derivative is negative or 0 throughout the domain, which is clearly true, because this term is obviously positive, right? We have 0 or positive on top and positive on the bottom, and then we multiply by negative, so it's going to be negative overall. So this is true. Okay. Let a, b be real numbers where a is less than b. Suppose that there are two continuous functions, bounded and negative. Then the area enclosed by f and g between x equals a and x equals b must be negative. Okay. I mean, you have some a and some b, right? Don't really need this. And we have two negative continuous functions that are bounded, like whatever. Between, I mean, should be true, right? I don't see why not. They didn't specify, like, if you calculate the area from here to here, it's negative, or from here to here, it's positive, or anything. I think they just care about the net area. Like, I guess what they want us to do is the area between. I mean, this is really just a formality or a technical question. So it depends what they mean. In general, like, you can think that regardless if this is f or this is g, this area should be negative, right? But if they want us to do, like, they say they don't specify which one comes first, actually, right? So, like, if they wanted the area, no, it should be true. Continuous, bounded, and negative, right? I mean, yeah. Oh, hold on. Yeah. Even if you had something like this, the area is this and this. It's all negative area still, right? Doesn't matter. Doesn't matter. It should be true. Okay. They want us to. Okay, so this is odd, right? And then we have this, I think, is even. This should be true, I think, because an odd function from minus a to a will have zero area, right? Because the areas will be opposite of each other on both sides. Let's just make sure that I'm right, and I'll show you why even times odd is odd as well. So let's say f of minus x equals x to the 4 times cos squared of minus x. that's the same as cos of minus x squared. And we know cosine is even, so we can just put x here. And then we see that this is an even function, right? This is f of minus x equals f of x. And sine of x is odd, right? And if you have, let's say, f is even, say g is odd, right? Then if you have f times g, let's say we put in minus x, right? We can rewrite f of minus x as f of x, and we can write g of minus x as minus g of x, right? That's equal to minus f of x, g of x. So we clearly see that the product of even and odd is odd because f of minus x, let's say this is h, right? H of minus x equals minus h of x, right? That's odd. So because we have an odd function that is always defined, and for minus pi to pi it's going to be 0, right? Okay. Let an contained in RB sequence provide a complete and accurate epsilon n proof definition for what it means for an to converge. Okay, so an converges if and only if for all epsilon greater than 0 there exists n greater than 0 such that n e z n greater than n implies that an minus L is less than epsilon for some LER. Okay, so what is this saying? This means that I can make an as close as I want to L by making the values I'm plugging into it sufficiently big, right? Bigger than some n greater than 0. And I need to make sure that I'm plugging in integers because it doesn't make sense to plug in this is like a discrete sequences, right? Okay. Let an equals that. By definition, prove it converges. Make sure to fully justify your work. Okay, so we should use the definition we wrote above. We need to prove this. So I'm going to choose my L choose. I'm going to guess, I guess. I'm going to guess that L equals 1. As n approaches infinity, the non-biggest terms will become irrelevant, and it's going to just be n squared over n squared, which is 1, right? So I have to show that an minus 1 can be less than any epsilon I want. So in order to show this, I'm going to first plug in what an is. And actually, minus 1 is the same thing as n squared plus n minus 4 over n squared plus n minus 4. So I can just subtract the denominator here. And these cancel, right? So then we have minus 2 minus n plus 4 over n squared plus n minus 4 less than epsilon. Yeah. I kind of want to make sure that the denominator is not 0. That feels maybe important because otherwise I change 1 to 0 over 0 and the whole thing kind of doesn't make sense. So say we want squared plus n minus 4 to be bigger than 0. because we can just make sure that the n we choose will give us this. So if we have a product of -4 and the sum of 1, that is not possible. However, we can see that if we choose n equals 2, we're gonna have we'll have 4 plus 2 minus 4, which is greater than 0. And we can see that for bigger n values, it's just going to be even bigger, right? Because n squared is increasing and n is increasing, so yeah. We can just make sure that n is bigger or equal to 2. Okay, so we'll keep that in mind. So we have this thing. So yeah, because we're choosing n to be greater or equal to 2, we can basically say that first of all, we can use absolute properties to flip the signs of the top, and then we have this. So we can find something bigger than it and make sure that epsilon is bigger than that, so it'll be bigger than this, right? By the transitivity of this thing, the inequality sign. So I can make the denominator bigger, the numerator bigger, and the denominator smaller. So for example, n is greater or equal to 2, right? And I can make the denominator smaller. Okay. So if I want to make n squared plus n minus 4n be bigger than 0, that's going to be a bit more complicated, I guess. So let's not try and do that. Need to make the denominator smaller. You can just say n squared minus 4 maybe. Right? So now I have 3n over n minus 2, n plus 2. So I can say that I can take the 3 out by absolute properties, so I have this. Right, by dividing both sides by 3. And now I just want to find some upper bound on this thing. I want to ensure that I mean, I can even leave the 3, right? Whatever. I want to make sure that I want to ensure that epsilon's bigger than this, so I'll find the upper bound on this, yeah. So let's say I'm choosing n to be bigger than 2, okay? So that means that n minus 2 is bigger than 0, and it means that n minus 2, let's choose n to be bigger than 3. we can do that. It doesn't mess with anything we did before. Then we have this bigger than 1. So then we have n minus 2 times n plus 2 is bigger than it's bigger than 1 times n plus 2. But we also know by this thing that n plus 2 is bigger than 5. So I can say that this is bigger than 5. Okay, but now I know that 1 over n minus 2 times n plus 2 is less than 1 over 5. So 1 over 5 is an upper bound. So I can say that n is less than 5 epsilon. So this I can choose to be my n. I choose n to be the maximum of 3 and 5 epsilon. And in order to prove, I say that we have to basically go backwards. So we have n greater than n, so greater than this maximum. It means that it's greater than both of these numbers, right? Which means that it's greater than, and we know that never mind, it's fine. Sorry, okay. Multiply both sides by 1 over 5. And we know that 1 over 5 was an upper bound on yeah, I see. Wait, what? Was an upper bound on, wait, 1 over? Okay. I'm sorry. Okay. First of all, I should have multiplied both sides by 3. That's my bad. Okay. And because n is greater than 3, we know this is positive, so the absolutes were kind of redundant. Okay. Sorry. Can I use my arrows? Okay. So then, since it was 3 over 5, this should be 5 over 3. Although, I guess 5 is fine, but whatever. Okay. It was an upper bound. We need a lower bound, no? My logic is that no. I see. I have n less than this, but I need n bigger than something. That's the problem. I see. That's interesting. We need to make sure that if n is bigger than something, this is true. Um, we actually know that n squared is more than n minus 2 times n plus 2 for when n is greater than 3, right? Uh, I could try and prove it, I guess. Um, so that we have n squared is bigger than n squared minus 4. Oh yeah, this is obvious, right? Yeah. So because of that, I can switch to that with n squared, right? And then I actually want to find a bound on the 3n. I want to find, an upper bound on the 3n. So we know that n is bigger than 3. That means, we want an upper bound on it. I think we should reciprocate here. Yeah, let's reciprocate here. This is greater than 0 because n is greater than 3. So we can say that n squared over 3n is more than 1 over epsilon. Now we have 1 over 3n. We want to find a lower bound on it, because then we want to say that n squared over 3n is bigger than n squared times the lower bound of 1 over 3n, which will be more than epsilon. So if this is more than epsilon, then with the lower bound here, then this will definitely be more than epsilon. So we want a lower bound of 1 over, this won't have a lower bound though. Oh, wait. The ends cancel. I'm so stupid. Yeah, I don't know what I was thinking. Okay. Yeah. You just have n over 3 is more. I overcomplicated this whole thing so much. Whatever. N more than 3 epsilon. Okay. So I should choose n to be greater than the maximum of 3 epsilon and 3. So then that means n is greater than 3 epsilon, which means that n squared over 3n is bigger than epsilon, which means that n 1 over, right? What? Sorry. Where did I do this even? Yeah, it was 1 over epsilon. So can't find. Oh, here, yeah. So we have something that looks. Okay, the 3 should be on top, maybe? Yeah. Okay. So we have this, then we can put the 3 in the bottom here. This is the same as that's why you should be organized when you do work. I don't even know. just saw it. Whatever. Oh my god, where is it? I don't know where it was. Here, n squared over 3n. Yeah, it's more than 1 over epsilon. Okay. So, we found that this is true. I see. So we can make this bigger by adding n and subtracting 4. Wait, what? Sorry. I guess I should reciprocate. They're both positive. So I have 3n over n squared is less than epsilon. So I have yeah, 2n plus n over n squared is more than 2 plus n minus 4 over n minus 2 times n plus 2. This is bigger, right, than this, so that's not true. I don't know why I did that. I have to make it smaller, right? I can't just delete the 4. Okay. I don't know what I'm doing. I see. Maybe. I see. I need to say that 3. Yeah, so I'm saying epsilon. Epsilon is bigger than this. Yeah, I want to say it's bigger than something. So I have to find somehow else to bound this part of it. So n squared minus 4 was fine, but I need to bound this from. I need to get something that's bigger than this. Sure. So I know that we're choosing n to be bigger than 3. So this is this function will be decreasing. So I can just plug in 3 and get 1 over 5 and say that 1 over 5 should be a upper bound of this, right? So then I can just say that Yeah, okay. Let's do the whole thing from the start. I'll do it really fast. Okay, I promise. Uh, yeah. What is it? N squared minus 2 over n squared plus n minus 4. Okay. So I need n squared minus 2 minus n squared minus n plus 4 over n squared plus n minus 4 to be less than epsilon. Okay, use absolute properties. Get this. So now I'll start making this bigger by making the denominator bigger. By making the numerator bigger, sorry, and the denominator smaller. Okay. Okay. Actually, I want to make the denominator bigger. Sorry, I want to make it smaller. So I want n squared minus 4n to be still positive though. But definitely it's going to be smaller. And that means I need n times n minus 4 to be bigger than 0. So I'll just choose n to be bigger than 5, right? And then I can actually just put an n here. And then I'll just have 2 plus 1 over n minus 4 to be less than epsilon. So I can flip both sides. N minus 4 over 3 is bigger than 1 over epsilon. And we're basically finished. N is bigger than 3 over epsilon plus 4. So then we just choose n to be the maximum of 5 and 3 over epsilon plus 4. And then working backwards, we have n is bigger than this, implies that n is bigger than this. This implies this, which 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 implies that a and 1 is less than epsilon. And that concludes the proof, okay? Sorry that took long, but yeah. Need to practice to do it right on the first try. Prove that that thing diverges. Okay. So I'll show that for all m greater than 0, there exists n greater than 0 such that any z n greater than n implies square root n is greater than m. So basically, I'm going to show I can make this as big as I want, which means that it will approach infinity. So I have this implies this, right? So I just choose n equals m squared, and yeah. Okay. that is a very easy proof, which was worth, okay, this was at least worth 8 marks. Okay, evaluate that integral. So first we should complete the square, and then we should use trig sum. So let's do that. So to complete the square, we need we need x minus a squared. There's a minus here, which is kind of throwing me off. Okay, I guess I can take out the minus, just factor it out to start with. Then I get x squared minus 4x minus 5. Now to complete the square, I need x minus a squared to give me x squared minus 4x. So clearly I'm going to need x minus 2 squared, which equals x squared minus 4x plus 4. So now we see that we can compare these two, and we see that we need this minus 9, right? So let's do that. Okay. I guess we can write this as 9 minus x minus 2 squared. Okay, so we want to get eventually 1 minus cos squared or sine squared, so we can then switch it to the other one and square root it. And doesn't really matter, but by convention we use sine, so let's do that. You could also use cosine, but I'll use sine. The reason why I put a 3 here, so when I square it I'll get a 9, which I can take out, so I'll have 1 minus sine squared, which is what I want. Derivative of sine is cosine. Yeah, I guess that's why it's the convention, so you don't have to deal with minus signs for no reason. Okay. Yep, looks good. Okay. And the dx changes to this. Okay, so we can pull out the 9, becomes a 3 when you take it out of the square root. We multiply with this 3, we get 9, and we can take that 9 out of the integral. This square root, it'll be the square root of 1 minus sine squared, which is the square root of cos squared by the Pythagorean identity, and the square root of cos squared is just cos. So you just actually have sec squared here. No. Sorry, not sec squared. You have cos squared theta, d theta. Because this thing will be cos theta once you pull out the 3, and okay, so now we have to somehow solve this integral. we can simply use the half angle or double angle identity to do this. We know that cos squared theta is equal to I mean, sorry. I know that cosine of 2 theta equals, right? Yeah, cos squared minus sine squared, but I can write sine squared as 1 minus cos squared, so it's minus 1 minus cos squared, that's 2 cos squared minus 1. So then you have cos squared equals 1 plus cos 2 theta over 2, right? So we should plug that in over here. Okay. Now this is pretty easy. The half just becomes theta, half theta, right? And the integral of cosine is sine, because derivative of sine is cosine. So it's just sine 2 theta over 4. Now, why is it over 4? Because first of all, we had over 2, and then we should use reverse chain rule to multiply by 1 over the derivative of the inside. So when we go to differentiate this, when the 2 comes out, it'll cancel with our other 1 over 2. So something like this, right? Now remember what theta was. Back when we defined it, we have theta equals sine inverse of x minus 2 over 3. Right? So, okay, I'm not going to remember this. Let's bring it with us. Okay. So, I should put in... Now, it's not good notation to leave it like this. For here, it's fine, right? There's nothing you can do. For this part, I should try to make it better. So we know sine 2 theta is 2 sine theta cos theta. And sine inverse cancels out, so just put what's inside. Now we have, that was sine, so now we have cos of sine inverse of theta. Okay, let's let this be m. So we know that m equals sine inverse. This means that sine m equals this one. Okay, so sine is opposite over adjacent. So draw a triangle. This is m, opposite over adjacent. No, that's tangent. Opposite over hypotenuse, sorry. Okay, make this 3, use Pythagorean theorem. 9 minus this squared. Okay. So we need cosine of m, that's this adjacent side over 3. So this whole thing is just and plus c. Now, one thing to note is that we have to set some intervals for theta, usually, in order for all of this to work. But, like here, we have the square root of cos squared. That's really the absolute cos theta times cos theta. So we kind of want to make sure the cos theta is positive anyway, so that this is fine. So cosine looks like this. So we want just this interval right here. We define x minus 2 to be 3 sine theta. I guess we should just say that theta is in this interval of, maybe we need this interval. I honestly don't know. Whatever. Some interval where cosine is positive, so then you can just remove the absolute value, right? Something like that. Okay, and then your final answer would be this. You can expand the 9 into it if you want to. Doesn't matter. Right? Okay. Next question. Answer exactly one of the two questions below. You get to choose which one you wish to prove. Points will not be awarded for work done for more than one question. Okay. Determine whether that one converges or diverges, or whether that one converges or diverges. Okay. Second one looks kind of easier to me. I don't know. I guess they're both improper integrals, but whatever. Okay. Arctangents look something like this. And these are pi over 2 and minus pi over 2. So if we're trying to integrate from 0 to 1, at 0 it's going to be 0 and x will be 0, so it will be improper there, but other than that, x will be positive and it will be positive. So this is very easy to just do this one. This is a type 2 improper integral. So it's going to be equal to the limit as a approaches 0 from the right, because it's the bottom of the integral, so we approach it from the right. A to 1 of x over x plus arctan x dx. Yeah. So we have to find the antiderivative of this thing. How do you integrate x over x plus arctan x? The question. Try and find the answer online. I'll be right back. Okay, so we should do this by parts. Yeah, we should try and differentiate this one. And we should integrate this one. Okay, so we get this, and we get hopefully I'm not making it too complicated. I am making it too complicated. One sec, I'll be right back. Yeah, so I just realized the question asked if it converges or diverges, not what it is. So I just wasted my time for no reason, but okay. Anyway, when I approach a zero, we can linearly approximate arctan x as x, right? So it's just gonna be half. I guess as I approach a zero, converges or diverges. I mean, for it to diverge, it would need to have like an asymptote, right? Which it doesn't. Maybe you could just say that this is, yeah. You mean, we could just say that this is continuous on 0 to 1, right? So there is, right? And then we also know that the limit as a approaches 0 plus this here the slope is just 1. It's like the derivative is 1 over x squared minus 1. Or sorry, plus 1. So if you put in 0, this is nothing. So our derivative is 1. So the linear approximation is x. So it's going to be at the limit it will be like basically exactly equal to x over x plus, well, if the slope is 1, then we should say basically f of arctan of 0 plus delta x is approximately equal to 0 plus the derivative, which is 1 times delta x, right? So arctan x equals x for small x, so we just put x here, and that is just equal to 1. So basically it's continuous, and there's no there's no asymptote, right? Because there's no asymptote, we can basically fill in the gap at half, and if we put that there, then we can actually do like this by defining a new function which will have the exact same area, and define it as a piecewise function where it's x over x plus arctan x when x does not equal 0, and it's equal to half at 0. And we know that this function will have the same area, and we know that under a continuous curve there will be a finite number of areas, so this converges. Okay. There's a lot of questions left. Okay. So I'll continue this in a new video that I'll upload soon, and I'll also go over the mock exam questions that I'm gonna go now to do mock exam. So yeah, see you soon.